Okay, welcome back. Now I'm going to do an example for the Carnot cycle, and then we're going to be asking a bunch of questions from it, and then we're going to be learning a lot of things from this. So the question says, a polyatomic ideal gas is to undergo a Carnot cycle. It starts in a chamber of volume 0.008 meters cubed and temperature 340 Kelvin and pressure 650 kilopascals. So this is, we're calling state 1, the initial state. So let's write that down. The initial volume is going to be 0.008 meters cubed. The initial temperature is going to be 340 Kelvin. The initial pressure is 650 kilopascals. Then it says it expands isothermally to a volume 0.00935 meter cubed. So we can call that state 2. So we'll call that V2, right? V2. So this one we'll just call V1, T1, and P1. Okay, since those are all the initials. V2 is going to be the 0.00935 meter cubed. That's what I'm calling state 2. While heat comes into the gas, it says. So the first process is always isothermal in the Carnot cycle, right? Then it expands adiabatically to a volume 0.0114, so we'll call that V3, 0.0114 meter cubed. So that's going to be state 3. So the second step is always adiabatic. Then it is compressed isothermally to a volume V4. V4 is not given, right? So V4 is not given. So that step is isothermal, while heat is extracted from the gas. So heat is expelled or extracted, you can say. Finally, it returns to its initial state in an adiabatic process. So I'm going to erase these, draw the PV diagram for this, and then we can ask a bunch of questions based on that, okay? So let's, okay, starts here. So the first process is isothermal. Isothermal all the way to a volume of, so the V1 is going to be 0.008, and then we'll call this one V2, V2 0.00935, okay, right there. And then from there, adiabatically, we go to 0.0114, so V3, so adiabatic is more steep than isothermal. Right, so this is isothermal, adiabatic, right? And then V3 is going to be 0.0114 meter cubed, okay? And then we're going to go back isothermally to V4. And then from there, adiabatically back to the origin, okay? So during the isothermal process, we're going to have heat coming into the gas, right? So we can call that Q hot, and then over here we're going to be calling that Q cold, that we're going to dump heat to the cold reservoir. So heat coming in from the hot reservoir, heat being dumped to the cold reservoir, right? So of course one of the first things we're going to have to do is then find out what P2 is, right? We want to find out what P2, we want to find out also the temperature here, T2, and then this one is T1, right? And then over here we want to find out P3, and we want to find out T3, right? The temperature over there. And then we're going to go back here, and then over here we want to find out P4, and we want to find out the temperature there, T4. So I like usually doing all that before I even begin the question, right? So these are going to be some of the questions that the problem is going to ask. It's going to say, how many moles of gas are there in this chamber? So how many moles? How many moles, okay, of gas? So that's the N value, right? B, we can say, what is the pressure, volume, and temperature in each state? So basically those are all the P1, P2, P3, all of them. So P2, P3, P4, and then we want T2, T3, T4, and then all the other volumes are given, right? And then, of course, V4, if we want to find out. V4 wasn't given, right? And then we want to see C. Then the question C is how much heat comes into the gas, the QH and the Q cold. What is QH and Q cold? Right? Remember during the adiabatic processes, which is process 2 and 4, right? We can call this here process 1, process 2, process 3, process 4. During 2 and 4, there is no heat coming in or being expelled out, right? Then the question D is going to be, what is the work done by the gas in each state and the total work done by the gas? So what is work done by the gas in each state? Work 1, W2, W3, W4, right? And then it says the total work done by the gas, the total work done, which we just add up all the works, right? And also the ideal efficiency of this engine. Ideal efficiency. The ideal efficiency is the Carnot efficiency, right? Ideal efficiency. So we can call it the maximum efficiency. Question E says, what is the change in entropy from state 1 to 2, 2 to 3, 3 to 4, and 4 to 1, and the total change in entropy? Okay, E. What is the change in entropy? What is the change in entropy? So from stage 1 to 2, stage 2 to 3, stage 3 to 4, stage 4 back to 1, right? So delta S1, delta S2, delta S3, delta S4, and then delta S total. Okay? And then question F says, if this process is run backwards, so now if we go this way, this way, this way, this way, this way, what would be the coefficient of power in the cooling mode and the heating mode? So if we operated this as a refrigerator or as a heat pump, right, and then we ran it backwards, what would be the coefficient of power? A, B, C, D, E, F. So COP of the heating mode of a heat pump, and what would be the coefficient of power if it functioned as a refrigerator? Okay, so a lot of good questions. So it all begins by calculating the number of moles and then the pressures, and then we can begin with the QH, Q cold, and then the work and all of that other stuff. Okay, okay, so then once you write that down, we can erase that, and then we can begin actually performing the calculations. Okay, so let's erase this portion. Okay, so let's find out the number of moles. We can easily do that by saying P1 V1 is equal to nRT1, right? So the pressure P1 is going to be 650 times 10 to the third. V1 is going to be 0.008, and then 8.314 is the gas constant, and then the temperature T1 is equal to 340 Kelvin. Okay, so that one is a pretty quick calculation. Okay, let's write that here. 1.83956 moles, right? And then we can begin to calculate the pressure, P2, P3, and so on, right? Okay, so then how are we going to calculate that? Well, the first process is isothermal, right? So we can say with an isothermal process, T2 is going to equal T1. So we can say here T2 also equals 340 Kelvin. Okay? So then, if that's the case, P1 V1 is equal to P2 V2, right? In the isothermal process. And then so we say P1 is equal to 650 kilopascal, V1 is equal to 0.008, P2 we don't know, and V2 is 0.009. So then I'm going to write that always on the top as we accumulate more data, right? So of course the pressure went down from its original pressure of 650, right? So P2 is going to equal 556.1497 kilopascal. Okay? So then, how are we going to do this? Now I want to find out the temperature T3 and then the pressure P3, right? So that process is adiabatic, so we use P2 V2 to the gamma, right? So the pressure P2 here times V2 to the gamma is equal to P3 V3 to the gamma. Okay, and then what is the gamma? Well, in this case, we're assuming a normal, regular polyatomic gas, so what would that be? We're going to have here the Cp and Cv. Cp of a polyatomic gas is 9/2 R, and the Cv of the polyatomic gas is going to be 7/2 R. So the gamma is going to be the ratio. Gamma is going to be the ratio of Cp to Cv, so it's going to be 9/7, right? So 9/2 R over 7/2 R, and then the R and R cancel, and then the 2's cancel. So we basically get 1 2/7. The gamma might end up becoming, because of quantum mechanical reasons, it might be slightly different, 1.29, 1.3, 1.26, 1.25. But in this case, nothing was given about the gamma, so we are assuming that a regular Cv of 7/2 R, Cp 9/2 R, and then so I'm going to use the gamma that you get by simply taking the ratio of those two, then you're going to end up getting 1.2857, right? So let's leave that over here, write that over here. Okay, so then I'm going to do my ratio thing. So P2, we got 556.1497, and then V2 is going to be 0.00935 to the power gamma, which is 1.2857. That's going to equal P3, which we don't know, times V3, which is 0.0114 to the power of 1.2857. Right? Well, what I can do is I can just bring everything to this side and then write 556.1497. Bring that volume here, so say 0.00935 divided by that volume, 0.0114, right? So I'm taking the V3, I'm bringing it down here, and so since they're the same power, I can first divide them, divide V2 over V3, right? And then raise it to the power of 1.2857, and then that's going to be P3. Okay? Decimal places to get more accuracy, 0.242 kilopascals. Then now I can find the temperature T3. The temperature is going to drop because this is not isothermal, right? So how do we do that? Well, we can say P2 V2 over T2 must equal P3 V3 over T3, right? So all of the pressure, the volume, and the temperature is changing, but the ratio of PV over T stays constant, right? So what are we solving for? We're solving for T3, right? So T3 goes over there, and that's going to equal T2 P3 V3 over P2 V2, right? So P3 V3 T2 over P2 V2. So then we have T3 is going to equal what? Let's put the T2. The T2 we got to be the same as T1, which is 340 Kelvin, right? And then P3 is going to be the 431.0242. V3 is going to be the 0.0114, right? Divided by P2, which is going to be 556.1497, right? And then V2 is going to be the 0.00935. 0.00935. Okay, so now I know T3, P3, V3. Then how about T4? Well, this is isothermal, so T4 is the same, right? So T4 is the same, 321.2788 Kelvin. But we don't know V4 and we don't know P4. There's two unknowns, right? How do we find V4, P4? Okay. Okay, so then how are we going to do that? Well, we know that this is isothermal, so that I know P3, V3. P3 V3 must equal to P4 V4, right? P4 V4, right? So I know P3 is 431.0242, right? That's kilopascals. Kilopascals. And then I know V3 is equal to 0.0114. Okay? And that's going to equal P4 V4. But I don't know P4 and I don't know V4. You see that? So then I can say, I can multiply that and I can say, okay, 588. But then the other one, we know that this last stage is adiabatic and it has to come back to the initial state, right? So we can use the equation for adiabatic. Then we can say, okay, P4 V4 to the gamma is equal to, back to the initial state, P1 V1 to the gamma, right? So then we can say here P4 V4, and then the gamma is going to be your 1.2857. Okay, P1 was what was given initially, 650 times 10 to the third, right? And then V1 was 0.008. 0.008 to the power 1.2857. Now this one is going to be a system of two equations, two unknowns. What I can do is I can substitute P4 is equal to 4913 over V4, right? So P4 is equal to 4913.67588 over V4, and then substitute it here into P4, right? So it'll be 4913.67588 divided by V4. Okay? So then what's going to happen? Then I can kind of work with this because now I only have one unknown, right? So I'm going to be erasing this. Okay? So then what's going to happen here? Well, you can bring the 4913 down there, and then V4 to the power 1.2857 over V4 is going to be V4 to the power 0.2857, right? So V4 to the power 0.2857, because you subtract 1 from here and only the decimal portion is left, right? Then you're going to multiply this, 650 times 10 to the third times 0.008 to the power 1.2857, right? Then you're going to divide that by the 4913, 4913.67588, right? So then I'm going to compute all of this and so forth, okay? So it's a decimal number. So then how do I get V4? Then I can raise both sides to the power of what? So then I can say V4 to the power 0.2857 raised to the power 1 over 0.2857 is equal to 0.2663849 raised to the power 1 over 0.2857. So on your calculator, all you have to do is just take this number that you got, the decimal that this number gave you, and then raise it to the power, and then put 1 divided by 0.2857. 0.2857. So the V4, I'm going to put it over here. V4, 0.00975 meter cubed. So let's see, does that make sense? Well, actually, it looks like V4 is actually larger than V2, right? So the graph looks a little bit different than what I drew here. It should look like this. V2 should be here, right? And then this one should look like this. V4 should be on the right of V2. So it's going to look something like this. Okay? Like this. and then this is V3. Then V4 looks like this. So V4 was larger than V2. Then from there, it looks like this. Something like that. So you see, this is isothermal, adiabatic, isothermal, adiabatic. This V4 is slightly to the right of the V2, which is possible. It just depends on the numbers that were given, you see. So we're going like this, like this, like this. Then what's left to do? How about calculating P4? And then once we did that, we get the answer. Okay, so then how do we get P4? We can say P4 V4 is equal to P3 V3, right? Which is the isothermal stage, right? So we can just do that way. That's the easiest way. So P4 times 0.00975, right, is equal to P3. We already knew 431.0242. Okay, and then V3 is going to be 0.0114. Okay. 503.9668 kilopascal. Okay, so does that make sense? P4, which is this one, should be larger than P3. P3 was 431 kilopascal, right? So it should be larger, but it shouldn't be as large as P2. P2 was 556 kilopascal. See that P2 is way over there. 556, so that makes sense. This is 503, quite lower, right? And then P1, of course, is the largest, which is 650. You see? Okay, so now we've got all the pressures. So what was question number, what was the next question? Next question was how much heat is extracted from the system and how much heat comes into the system. So the QH. The QH, how do we calculate that? Well, when the process is isothermal, the QH is just equal to the work done by the gas. Work done, which is in stage 1. Delta E of the gas is 0, right, in an isothermal process. So what is the work done? It's, right? So all we have to do is to take the number of moles that we got, 1.83956. 1.83956 multiplied by 8.314. Multiplied by the temperature. What temperature? The temperature of the hot reservoir, which is T1, right? So T1 would be 340 Kelvin. Right, so this is the hot reservoir, 340 Kelvin. And then ln of what? The volume V2 over the volume V1, right? V2 over V1, okay? Okay, now how much heat goes out of the system, how much heat is expelled in the second isothermal process, the Q cold? Well, the equation is going to be the same. Of course, the Q cold is going to be negative. So it's going to be the moles of gas times 8.314 times the temperature of the cold state here, the T3, right? So the cold reservoir, what is that? The T3 was equal to 321.2788 Kelvin, and remember T4 is the same, so we basically have one cold reservoir here, right? So the temperature here is going to be 321.2788. So then in this equation, we just change it to Q cold, 321, right? 0.2788. And then the ln, we take ln of what? V4 over V3, right? V4 over V3. So V4 is going to be what? V4, we put it over here, 0.00975. And then V3 is going to be the 0.0114. So if you go over 3 decimal places, 1, 2, 3, you get a ratio of 9.75 over 11.4. You take ln of that, and then you're going to get negative. What you could do is just basically reciprocate it and then take the absolute value, and then we already know Q cold is negative, which means it's being expelled out. So then we just express the absolute value of it, right? So we just take, okay, so then the work that the object, the work that the gas does in stage 1 is equal to the heat Q hot. So we can say W1, because the next question was, what is the work done by the gas in each stage and the total work and the ideal efficiency of this engine, right? So the work done in stage 1 is just going to be Q hot. So we can say W1 equals this, okay? And then the work done in stage 3, right, going back is going to be negative. So it's just going to be that, but it's going to be a negative sign, right? So we're just going to say W3 equals negative of the absolute value. Since over here, we recorded the absolute value of the Q cold, which meant it was already negative, but I just recorded the absolute value. So then the work done is going to be the negative of the absolute value, which is just simply to say the work done in stage 3 is equal to the heat Q3, right? So then that's W3. Now let's find W2 and W4. What's the work done in the adiabatic process? So we can say W2 is going to be equal to integral P dV. And then remember that P is equal to PV to the gamma is a constant in an adiabatic process, right? So we have P is equal to a constant over volume to the gamma power, right? So then you're going to say here, this is a constant over V to the gamma dV, right? So basically you're taking the integral of this stage right here. Constant over V to the gamma dV. So then what is that integral? Well, what is the constant? The constant is the one that stays the same. It's the P2 V2 to the gamma, which is the same thing as the P3 V3 to the gamma. So the constant is the P2 V2 to the gamma, right? So W2 is going to be P2 V2 to the gamma. The constant comes out of the integral. And then you integrate this dV over V to the gamma from where? From V2 to V3. V2 to V3. Okay? So that's going to give you W2. Okay? So what is that equal to? Well, integral P2 V2 to the gamma, the integral of this, that's a V to the minus gamma, right? V to the minus gamma dV. And then when you integrate this, you get V to the minus gamma plus 1. V to the minus gamma plus 1 over minus gamma plus 1, right? And then you're going to have, you're going to integrate this from V2 to V3. So then what you can do is you write down what the gamma is. So we have here W2 is going to equal P2 V2 to the gamma, right? And then on the bottom we have here 1 minus gamma, so 1 minus, right? And then the gamma was 1.2857, 1.2857, right? And then this one you reciprocate it back down, 1 over V to the, and then when you reciprocate it back down, this becomes gamma minus 1, right? Gamma minus 1. So it becomes gamma minus 1, 1.2857 minus 1 from V2 to V3. Okay? So then you have here W2 is equal to P2 V2. Now we can actually put down what these values are. P2 is going to equal 556.1497 times 10 to the third power. Right, that's P2. V2 is going to equal 0.00935. Okay, so then I'm going to erase this. 0.00935 to the power gamma, which is 1.2857, divided by 1 minus this is going to be negative 0.2857. Right, and then when you integrate this, you're going to have 1 over V to the, this is going to be 0.2857, so V3 is going to be 1 over 0.0114, right, that's my V3, to the power 0.2857, right, because you subtract 1 from here, minus 1 over V2 is going to be 0.00935 to the power 0.2857. Okay? Now what you can do, this minus sign, we can change the place of this, change the order, right? And then you're going to have plus, minus, and then that's going to be your work done in stage 2, the adiabatic process, right? So it's going to be, then we already have W3, which is going to be negative 768.233. Then going back, it's also going to be negative, right? So then how do we do it? Well, we could just change a couple stuff here. Then we don't need to completely redo the whole integral, right? From here to here. So what stays the same here? From here to here, it's going to be P4, V4 to the gamma equals P1, V1 to the gamma. So over here, I could either use P4, V4 to the gamma, or I could use the original number P1, V1 to the gamma, right? Because from here to here, P4, V4 to the gamma is the same as P1, V1 to the gamma. So let's just use P1, V1 to the gamma. This one will stay the same, right? And then over here, we're going to go from where? From V4 to V1, right? From V4 to V1. Right, so that's the only thing that changes. 650 times 10 to the third, and then we put V1 is 0.008, and then here I'm going to change it to V1, which is 0.008, and then over here I'm going to change it to V4, which is 0.00975. Okay. So now, it's interesting that it came out to be negative of pretty much the same thing as W2 is. Let's see if that is a general rule that will always happen, or is that just a coincidence that happened in this case? Let's see what's happening here. Okay, so if we add up all the work done by the gas, remember for heat engines we said a certain amount of heat comes in Q hot, and then the engine does a certain amount of work total, and then you extract some heat Q cold. So, right? So that should always be true. So in our case, what was the Q hot? The Q hot was 810.86. The work total we could say is W1 plus W2 plus W3 plus W4. Right? That's the total work done, plus the Q cold, and then in our case, Q cold was 768, 8.233. So over here, when you put Q cold, you have to put the absolute value of it. In other words, that's already considered that you're dumping it, even though Q is actually negative. But since we're already assuming that you're dumping that heat, here you put in the absolute value of it, the 768.233. So then what's the rule here? So 810.86. We already said that W1 is exactly identical to QH because this is an isothermal process. So it's exactly the same. 810.86, right? And then W2 is the 1002, right? W3 we said exactly identical to 768, but it's negative of it, right? Because the work done is negative in the third stage. So it's negative 768. Negative 768.23. And then W4 is going to be what? Negative. Negative 1000 plus 768.233. Okay? So then what do you notice here? 810 is exactly equal to 810, so that kind of cancels, right? And then negative 768, which is W3, cancels the 768. So then W4 should always equal, in a Carnot cycle, should always equal exactly negative of the W2, right? So in theory, we shouldn't even have to necessarily calculate it. We could just say W4 is equal to negative 1002.1845. The only reason it comes out slightly off is that when we're doing calculations, we're not going to many sig figs. We're not going out to many decimal places. So once you have a problem like this, you can just, once you calculate W2, you can just assume W4 will always equal negative of it. This will cancel this. W1 will equal QH, and then W3 will be negative of this, so then this will cancel this, and then the general equation for heat engines will always hold, okay? So then let's just assume W4 is exactly identical, and then it's equal to negative 1002.184, okay? Okay, so then now what's the ideal efficiency of this engine, okay? What is the efficiency of this engine? So the efficiency of this engine is going to be 100% times the work done, the total work done by the gas divided by the heat coming in. So what is the total work done by the gas? 810.86. 810.86 minus 768.233. The W2 and the W4 cancel each other. That's the total work done by the gas, which graphically represents the area under this graph, right? The area under that graph. So then you divide that by what? Q hot, which is equal to 810.86. That's the efficiency of that engine. Okay, now, we can show this equation to also give you the same answer. Remember, since this is a Carnot cycle, we can also use the Carnot efficiency equation. Carnot efficiency, we can say efficiency Carnot is equal to 100% times, remember, work over Q hot. But then we can say work is equal to, remember the equation, Q hot is equal to work plus Q cold. So the work is equal to Q hot minus Q cold. So we can say Q hot minus Q cold over Q hot. So then we can change that to T hot minus T cold, right? T hot minus T cold over T hot. Okay, so since this is a Carnot engine, this should give you the same efficiency as this, right? So when I subtract the two temperatures, I can just keep them in Kelvin or Celsius. So since I already have the two temperatures in Kelvin, the T hot is going to be 340 Kelvin minus the T cold, which is 321.2788. So notice the reason this engine was not too efficient, the difference in the two temperatures of the hot and cold reservoirs was too close to each other. They were only off by about 20 Celsius. So you don't want an engine where the hot and the cold are too close to each other. You want it to be more spread out so that the hot is really hot and the cold is really cold, okay? So that's why it wasn't a very efficient, efficiently running engine. Then you divide that by T hot, which is equal to 340. Then you multiply that by 100, right? So efficient. Notice it's not identical to this, but again, that's because of rounding error, right? Rounding error. So which efficiency is the more correct? Well, probably there's a bit more rounding error in the Q hot, Q cold, rather than the temperature. In the temperature, I didn't really do too much rounding. I probably accept this result more, or I could argue this result, I accept that result, or I can take the average of the two. It doesn't really matter. So my answer can be either one. So let's just say the efficiency, I'm just going to accept 5.51% efficient. Just take the efficiency as derived from the Carnot efficiency. But if I hadn't rounded at all, the two would be exactly identical. So we will have proven that QH minus QC over QH is exactly equal to TH minus TC over T hot. You see. Okay, so then the next question was, what is the change in entropy of this gas between state 1 to state 2, state 2 to 3, and so on, right? So the state 1 to state 2, the change in entropy, well, for isothermal process, since the temperature stays the same, the change in entropy is always dq over T and an integral of that, right? But since isothermal, this is isothermal, the temperature stays constant, so we just have 1 over T dq. We can factor the temperature out of the integral, and we just have 1 over T integral dq, right? So integral dq is just going to be delta q. So that means the change in entropy is just the hot temperature coming in over the hot reservoir, right? delta QH over T hot. So you just basically divide the QH 810.86 divided by the temperature of the hot reservoir, 340 Kelvin. So you're dividing QH by TH. 810.86 divided by 340, you get 2.385. 2.385. So let's record that here. 2.385. That's joule per Kelvin. That's the units of entropy. So the entropy of the gas increases by 2.385 joules. Now, in an adiabatic process, there is no heat coming in, and if it's done reversibly, quasi-statically, slowly, and no heat is coming in, the change in entropy is 0. Okay? So during stage 2 to 3, no change in entropy, because delta Q is 0. Then going back, I'm going to use a similar equation, but now the entropy of the gas is going to decrease. When I make a gas colder, by expelling heat, the gas is cooling down. Its entropy is now decreasing because the molecules are moving slower, right? So the change in entropy from stage 2 to 3 is going to be QH, Q cold over T cold, right? And here I'm going to write down Q cold as a negative. In other words, because I'm dumping the heat out, right? So then it's going to be negative 768.233 over T cold, which is 321.2788. Now here's how you can know if you've done the problem correctly. When I take this ratio, if it comes out to be close to this but negative of it, then the answer is good, because the total change in entropy of the whole cycle should be 0. Because the change in entropy between the third and fourth stage is 0, so I should come back and return back to the original state, right? So if you do 768, okay, so it's slightly a little bit different, but it should exactly be the same. So I'm just going to assume that this answer is that or that answer is that, okay? Just change them. Okay, so the answers were pretty close, and it proves that the change in entropy is the same. So that for the change in entropy between 2 and 3 and 4 and 1 is 0. So the total change in entropy of the gas of the whole stage is 0. Okay? Okay, this remains now the last question. It says, if the process is run backwards, so if it's running backwards this way, right? Running backwards this way, then what changes? Instead of the gas doing work, now I will be doing work, right? So I will be doing work on the gas, and then there's going to be, so it's basically going to be reversed. So remember the equation for a refrigerator or a heat pump. I do work in, and then this is T cold, this is Q cold, and then this is Q hot, and then this is T hot, right? So if I run it as a refrigerator, then the coefficient of power is going to be the how much heat I was able to extract from the cold reservoir, right, divided by the work that it took, right? Work in. And then if this is as a refrigerator. If I run it as a heat pump, then it's going to be how much heat I dump to the room, right, Q hot, over the work in. So if I run it backwards, what is going to be Q cold? So Q cold is just going to be just this number, right? The Q cold, 768, right? So the coefficient of power run as a refrigerator is going to be, Q cold is going to be 768.233. Divide that by, right? So I'm taking this number, dividing by the total work that I had to do on the gas. So it's going to be the difference of these two. Remember, that was the work done by the gas. 810 minus 768. Now that's the work that I'm doing on the gas if I reverse the process, right? So then it's going to be 810.86 minus 768.233. Okay? Now this actually becomes a good refrigerator. It's not a good engine because the efficiency is only 5%. But it's actually a really, really good refrigerator. It has a very high energy of power. Look, I only have to do a little bit of work, right? the work that I do is maybe what, 50 joules, but I'm able to extract 768 joules of energy from the cold reservoir. Wow, this is a really extremely good refrigerator. As a matter of fact, this is really very high energy efficient refrigerator. So it wasn't a good engine, but it was a great refrigerator. Okay, so how about the coefficient of power in the heat pump mode? Okay, coefficient of power in the heat pump mode. So then you're going to do, instead of Q cold over this, you're going to do QH over this. Okay, QH over the work. So 810.86 over 810.86 minus 768.233. Remember, when I did this kind of problems before, we noticed that the coefficient of power as a heat pump is always one value larger than that. So it should come out 19.02, right? So beautiful, right? So it's, as a heat pump, it's really good. As a refrigerator, it's really good. But as an engine, it's very low efficiency. So with this example, you can see the full range of the questions we can ask. The number of moles, the work done by the gas, the efficiency of the gas, all the different V3, P3, V4, using the polyatomic gas, the gamma of the gas. So it includes a lot of stuff in there. So review this, keep reviewing it, and I hope you learn a lot from this problem, okay? Thank you very much.